Hi everyone, this is going to be a video walkthrough of Spring 2021 CS61B Midterm 2 Question 5a. So for this question, we are given an initially empty hash table with 32 buckets and does not have the resizability. So we can assume hash table starts empty for each of the subproblems, and we do not assume anything about how the items are spread out given their hash code. Okay, so for question 1, we're asked to figure out the minimum number of items that will be in bucket 0 if we insert 16 items into the hash table. For this question, because we do not assume anything about how the items were spread out, we can think of the case of hashing all the items into buckets that are non-zero. In that case, will result in the minimum number of items in bucket 0 being 0 items. So this will be, to illustrate it in a diagram, this will be essentially hashing all the items into, for example, bucket 1. In that case, we have nothing in bucket 0, so the minimum number of items in bucket 0 will be 0. Okay, so the second question is more of the opposite of question 1. We are asked to figure out the maximum number of items in bucket 0 if we insert 16 items. So in that case, the hash table starts empty. And to maximize the number of items in bucket 0, we can think of the case where we hash everything into bucket 0. So in that case, we essentially hash all 16 items into bucket 0. Okay, so the answer for question 2 will be 16. So for question 3, we are asked if we insert 4 strings into the hash table and each bucket is stored as a binary search tree. So instead of having the usual linked list as the underlying implementation, just like how we learned in lab, we can have binary search tree as the underlying implementation for each bucket. And we're asked how many total string comparison operations will occur to complete these insertions in the worst case. So in other words, we want to maximize the number of comparisons we do in the binary search tree. To do that, there are 2 things we have to, it has to satisfy in order to maximize the number of comparison operations. The first thing it has to maximize is maximize the number of items that are hashed into the bucket where we are doing these comparisons. So maximize the number of items in one bucket so that we can have as many string comparison as possible, okay? And the second thing is we want to essentially see how we can maximize the number of comparison in a BST in that bucket, okay? So to satisfy the first condition, we essentially want to map all the 4 strings into the same bucket, okay? So now the question is reduced down to how many comparison maximums do we have when we insert 4 strings into a BST. So let's just try to count the number of comparisons in the worst case when we insert each element. So 1, 2, 3, 4. Okay, so initially the hash table is empty, so we don't really have anything in the tree to compare with. So when let's draw a tree here. When we insert our first element, we don't really have any comparison because it is the only item in the tree so far. So it's 0 when we insert the first element. So when we insert the second element, we'll compare it with the root. That's the maximum number of comparison we can do. So we'll insert it to any of the random size. It doesn't really matter. So for 2, we have 1 comparison. Okay. When we insert the third element, note that a key is we always insert into BST as a leaf. We always insert at the bottom level. So in this case, in order to maximize the number comparison, we'll compare with the root, and because we want to maximize it in this case, we also will compare with the leaf that we just inserted when we insert the second element. Okay, so in that case, there will be 2 comparison maximum when we insert a third element, and we don't really care which side it adds to. Okay, this is better than inserting the element here, because this wouldn't inserting it at the same level as the second element wouldn't give us the maximum number of comparison we want. Okay, so similarly, when we insert the fourth element, we will compare with the root, and to maximize it, we'll also compare with the root's children, and lastly, we'll compare with the grandchildren. So in that case, the maximum number of comparison we have for the fourth element is 3, and we don't really care where it's inserted. So in total, we'll have 0 plus 1 plus 2 plus 3, which is 6 number of comparison in the worst case for question 3. Okay, so this concludes the walkthrough for question 5a. Thank you all for watching.